Very good. Who has used a Bolt service with a credit card? Right. Who has attempted credit card fraud on Bolt? Okay, let's have a chat later with Elisaveta, maybe, who's gonna tell us about how do we do the machine learning to detect you guys. Welcome.
Hello, everybody. Thank you all for staying here for the last talk on this sunny, warm evening. And thank you everybody on Zoom still listening to us. I really appreciate it. I'm Elisaveta. I'm part of fraud data science team. I worked at Bolt for almost 4 years. Today, I'm going to share with you my experience of applying machine learning and fraud, and I will tell you how to succeed and how to build good fraud machine learning models. I will start describing what kind of fraud system we built at Bolt and how machine learning fits there. The main part of my presentation will be about specifics and caveats of ML, and I will tell to you how to overcome them. And at the end, I will share with you why A/B testing and fraud is important and why sometimes you allow fraudulent orders to happen. But this fraud was already sounded for many times. Now it's time to clear once and for all what actually I mean by fraud. At Bolt, we are facing payment fraud, and two main types of it are failed payments and chargebacks. So failed payments happen when there is not sufficient funds on user accounts. It means that when our write happens, when some order happening, we cannot capture money, and because there are no money on users' accounts. Chargebacks, it's like a bit different story, and let's consider this example. Fraudsters steal some card, and they are making both order with this stolen card. At the moment when order is happening, everything looks good from our side because we can capture payment. We can take money from this user. But after some time, we receive notification from banks that actually a real owner of this card disputes the transaction because real owner didn't make this right. And in this case, we need to return this money to actual owner, and we lose this money. So this type of fraud which we are fighting against. Now it's time to look at what kind of fraud system we've built at Bolt. Bolt exists for more than 8 years, and the fraud team hasn't started from the beginning. But during the last 4 years, fraud system became quite mature. Our team is very small, especially compared to size of our business and to team sizes of our competitors. And that's why we want to be as efficient as possible. And that's the reason why we automate as much as possible, and that's how Fraud Engine was born. It has two main parts. These are like fraud rules. It's the first part. We have a team of smart fraud analysts, and they discover fraudulent patterns, and they create manually fraud rules. Each of these fraud rule has its own score, and then it goes as separate elements to total fraud engine score. Another part of fraud engine is a machine learning model. For each incoming order request, it returns probability of how fraudulent orders are, and then this prediction converted to score, which also goes to as an element to total fraud engine score. So when order attempt happens, it goes through fraud engine, and then fraud engine outputs total score. If total score is less than threshold, orders get through, so basically it's happy path. A user can make an order. But if total fraud engine score is more than threshold, we predict that it's fraud, and we do not allow this to happen. We reject such order. So that's our fraud engine, and now it's time to have a closer look at machine learning part. Here I'm giving you example of our fraud prediction model, which we have in rights business, but similar setup exists in all other domains as well. Our model is YGBM model. Who of you heard and who of you know what actually YGBM is? Okay, at least half of you know. But if you heard about XGBoost or CatBoost, you understand what you can understand what YGBM model is. But it's a machine learning model, and it belongs to gradient boosted trees family of machine learning models. We've chosen this type of model mainly because it has a very low latency. Our orders are happening in real time. So all user open an app and they want to request ride as soon as possible. They don't want to wait a lot. And the LightGBM has like pretty good latency actually, and rider fraud prediction model on average has about 50-60 milliseconds. It's quite low. There exist other algorithms which proven to be good for fraud cases, like neural networks or graph machine learning models, but in reality, they might have a low latency, and we are not using them, maybe yet. Our model has more than 80 features. It's a different characteristic which we gather about user history, how users use the rides, delivery scooters, how users are connected among each other, different information about cards, payment methods, devices, basically everything which we can use to predict fraudulent patterns. What's also was already mentioned during this evening that this model as well, it's city specific. So we have this partition by cities. Although I'm talking like about one model, fraud prediction model, in reality, it has many artifacts. So we have a separate model for Tallinn, Riga, Paris, London. We take data for one city, train model for this city, and then all requests for this city are sorted only by this specific model. We operate in many different countries and markets, and they are like very different in terms of like where they're located and what market stage they are. And that's why fraudulent patterns are different as well. And that was the reason why the city-specific setup showed to us better performance compared to one big global model. Now, let's move to the main part. What actually like specifics of applying machine learning in fraud? I've started to work with fraud team about 2 years ago, and when I switched domains, I discovered that actually like working in building machine learning in fraud is quite different from what I did before. So here I highlighted 5 bullet points, and now we will look at each of them one by one. So first thing is that highly imbalanced data. When you build a classification model, you want your classes to be as balanced as possible. But let's say we have a 1% fraud rate. It will mean that we have only 1% of fraudulent class and 99% of non-fraudulent class in data. It creates huge disbalance, disproportion, and it makes for model harder to learn and to find patterns. The main methods, the most common methods which exist to tackle this are oversampling and undersampling. So with oversampling, you artificially increase the size of your data set, and you're trying to oversample smaller class, fraud class, to match size of bigger class. In the opposite, with undersampling, you downsample from bigger class to match the size of smaller class. When we experimented, we found that like for our data, undersampling actually performs better, because even if we reduce size of the final data set, we still have enough data points to train YGBM model. But we didn't stop at just like traditional undersampling approach. So usually you have this like when you with traditional undersampling, you have 1-to-1 ratio. So you want to make your classes similar size. But what worked better for our models is the N-to-1 ratio between resampled classes. So bigger class is still slightly bigger, but disproportion decreased. And it could be 1.5, 2, 3, 5, it depends on city. And actually N, it is now like additional hyperparameter which we tune when training YGBM model. Next point, what's specific about ML in fraud. Remember this imbalanced data, and it's actually influence what kind of metric you can choose for model training and for other things. So if you have this 1% of fraud rate, 1% of fraudulent class, it will mean that our model can be 99% accurate and still predict only good orders. So basically, you can see this high performance in terms of accuracy, but in reality, model will not predict anything. It will give only one value always. It means that you cannot rely on accuracy, and you should be very careful what kind of metric you choose. And it's always important. It also influenced by the fact that cost of model errors are different. So during classification problem, your model makes errors, false positives and false negatives. So false positives happen when we block good user. So it means that we predict that it's fraud, but in reality it was a good user. And costs here will be missed revenue. And let's say we have an order with a 10 euro price. It will be this 10 euro price multiplied by business margin, by profit which we take from order price. With false negatives, it's a bit different. So false negatives happen when we accept fraudster. So we predict that it's good user, but in reality it was a fraudster. And the cost for us here is just lost money. So the whole order price, so the whole 10 euros we will lose with this case, and maybe chargeback fee if applied. So you see, if let's say our margin like 10%, our cost will be here 1 euro. With false positives, and with false negatives, it will be 10 euros. So it's a 10x difference between these errors. And especially it's important to think about it and to adjust when you're working with a probability threshold to define where is prediction for fraud and non-fraud. Another point is change in data labels. What is it? Let's imagine that yesterday some order happened and we capture payments for this, everything was successful, we mark it as a good order. But today we received notification from bank that actually it was a chargeback. So what happened now is that we need to change this label from good order to fraudulent order. And if we train a model somewhere like yesterday as well, and we took this order in our training data set, it means that model used wrong data. And wrong data will lead to wrong model, and we don't want like bad models working into production. So to overcome this, what we are doing, we are analyzing when most of chargeback comes. So we analyze when we have majority of chargebacks are known, and in this we use this period to understand what kind of data we can use. So let's say in 3-4 weeks most of chargeback comes. It will mean that we cannot use 3 or 4 weeks of data in our latest 3-4 weeks of data on our data set, because during this period data labels can change and we cannot rely on them. Next point is a long feedback loop cycle. It's actually connected to previous point of changing data labels. By feedback loop, I mean how often we can experiment, how often we can do some changes for models, for our rules, and so on. Let's say we launched A/B tests, it started, then it ended. And at the moment of test end, we actually cannot analyze results and make decisions based on that, because we will see numbers, but they will change in the future. And we can do analysis only at some point in the future. And we use the same approach, the same as analysis of chargebacks, to define when we can actually analyze results. 100% true data only comes in 4 months, and it's very long period, and when we want to move faster, that's why we kind of use this approach of analyzing chargeback periods. And last but not least, when you are trying to figure out how to build machine learning model, you need to really think how it interacts with the whole fraud system. As mentioned in the beginning, our machine learning model works in parallel with rules. But maybe sometimes you want to use your model before rules or after rules. Maybe serving part is very expensive and you want to reduce number of requests which comes there, and you want to have your rules first and only then model. Another point here, it's always depends on your business type, what kind of latency you can allow for your users to not create too much friction. So for us, latency is important. But maybe for some e-commerce website, when users spend hour choosing some product to buy, probably they can wait additional like 1 to 2 seconds when before their order will be confirmed. And maybe for such cases, you can use more like complicated, deep neural networks, which will return prediction a bit longer and maybe a bit more accurate, and it will not create high user friction. So now we know like how to build a good fraud machine learning model, but how to define that it actually brings impact to the company. How to define that it's not only blocking fraudsters, but also not blocking good users. For this to understand, let's see what kind of impact we have in all of these our groups of, like this classification matrix, and there we have 4 groups. We already touched what are false positives and false negatives, but there are 2 additional groups of true positives and true negatives. So we know impact of false positives, it's missed revenue, impact of false negatives lost money. What true positives are, it's where we correctly predict fraudsters. So we predict fraudster and we block it. Impact here are saved money. So with a 10 euro price, it will be 10 euro saved. True negatives are when we accept a good user. So when we predict that it's good order and actually it was a good order happening. Impact here is again revenue, and for 10 euro order, it will be 10 euro multiplied by margin. So to calculate impact of the whole system, we need to combine each of this group, and you see that each of them has different formula how to calculate them. So to correctly estimate impact of model, we need to clearly distinguish between these groups. But when we started to think about it, we found this. So when order request goes, when we predict that it's not fraud, we are not blocking this, order happens, and then we see where we capture payment, where our true negatives are, and where we had some payment issues, it means that it was false negatives. But when we predict that it's fraud, we block this order attempts, and actually no order is happening, and there it's true positives and false positives altogether. And in this case, in this setup, we block all these order attempts for predicted fraud, and we cannot distinguish between these 2 groups. But if you see like here, true positives and false positives, they have different formula for impact calculation. It means that if we cannot distinguish them here, we cannot correctly estimate the impact. So what we decided to do, we decided to do A/B test and introduce control group. So our A/B test split is going there. Treatment group, it works as before, as described on previous slide. And what happens in control group? When we predict that it's not fraud, we do not block such order. Order happens. We've seen it before. We distinguish between true negatives and false negatives. But when we predict fraud, we are not blocking this order attempts in comparison to previous setup. Order happens in this case, and then we see where we can capture payment. It's our false positives, and when there are payment issues, it's our true positives. So when we allow this sum of small percentage of fraudulent order to happen, we can clearly see where we make mistakes and where we correctly predicted fraud. So when we are doing this, we can clearly estimate the impact of fraud system. And so, yeah, like when we analyze this A/B test results, we can gather this data and we can use it for different use cases. First, as mentioned already, we can measure impact of fraud system. It can be only impact of machine learning model, only impact of rules, or combined. Another thing that we can get estimation of real fraud level. So if before we only knew about this part, about false negatives, now we also about true positives. And actually, like this part is quite larger than previous one. So like we can understand what would happen if we would not have fraud system built. So basically, we can show like why this fraud engine is so important. And also remember that each of our rules has different scores. And we use this data from A/B test results to actually do fraud rule score optimization. It's a topic which requires additional presentation, so maybe sometime in the future you can visit us and hear more about it. Now, what are takeaways from my today talk? I'm sure now you learn about specifics of machine learning and fraud domain. Now you know how to deal with them and how to build better models. Also now, I hope you understand why you need A/B testing and fraud and what you can do with results and how you get estimation of your machine learning model's impact. Thank you for your attention, and now it's time for questions.
Okay, a lot of interest about fraud. Okay, I saw there first. We'll get here as well.
Thank you. Really interesting talk. I was wondering, maybe kind of if we're thinking in, let's say, production use cases, kind of maybe considering that, let's say that the theme of the talk that you guys can kind of configure things on the city basis. For example, how do let's say, tweaking of thresholds and the risk appetite, and how do you manage that in production, like per city level and stuff like that?
I mean, it's done by city. So also like this threshold, which we use to split predictions in fraud and non-fraud, it's adjusted by city. So everything just runs in parallel. We define what we are interested in, what we want to tune, and it's done for each city separately. And so.
You accept also different risk appetites.
This usually when we are talking about this risk appetite, we are talking about company level. So and here we kind of optimize for the whole system, and it's quite different. So we train machine learning models, but then we are doing this kind of optimizations. Optimization is done on a global level, so it's not per city level.
Good. We had. Let's spread out a bit.
Hi, thank you very much for the talk. I wanted to ask what % of users is blocked on average?
I mean, fraud is so sensitive domain, and we cannot disclose these numbers.
Thank you.
But yeah, it's a very interesting question. If you would work at Bolt, you would know.
Great. Let's take back as well.
Hey, thank you for the talk. I was wondering, so in A/B testing, so you let the fraud through, right? So I was wondering, do you know if that affects the kind of data you get? Like fraudster gets away with it, does it again, or is there any specifics to dealing with that kind of thing?
Do you mean that are fraudsters aware that we are doing A/B testing? Or
well, no. I mean, like if I get blocked, I'll probably not order again. But if I get away with it, I might order again with that stolen credit card or whatever. Is that an issue or?
It's a very interesting question, and we kind of experimenting with this setup because some fraudsters they can create hundreds, thousands of different accounts, and at some point they can find this way how they can get away with it. But we have tools to combat with it as well. So because if fraudsters understand that they can get away with it, they can do their fraudulent activity, we can lose a lot of money. But we wanted to understand the impact, but we don't want to allow a lot of losses to happen, and we have a tool to tackle with it as well.
Just inserting a bit of a commercial announcement here that Elisaveta is actually hiring another data scientist in her team in Tallinn.
So if you wanted to know actual numbers about fraud, you can apply for us, and then you will know.
But we have some time for more questions.
Thanks, Elisaveta. It was quite interesting about the imbalance problem, and you found that actually not having it 50-50 or in the same ratio was more beneficial for you. Have you wondered why this is? It's a little bit counterintuitive, but maybe not.
I mean, usually it just depends on what kind of data you have, and we've watched some lectures from Jan LeCun about deep learning, and at some point, point of videos, he just said, "Okay, it just works." And nobody can explain it why. Nobody can explain the math behind. And I would say, you just experiment with your data and you find a way what works better for you.
Yep.
I don't know if this is the same question from Heido, but the great talk. Thanks a lot. So I was very interested in the feedback loop that you analyzed and the changing labels. So assuming there are some percentiles that you find for this changing labels, and like there's some probably threshold that there's some let's say trade-off postponing to let's say not use the recent data and use recent data, but the effect is there are some changing labels, right? How did you analyze that? Did you just take median, or like what's the risk appetite there as well?
So yeah, it's very interesting questions, and it's usually the trade-off. So if you're not using fresh data, we are losing this information about recent fraudulent patterns, and kind of we are like trying to understand when it's like this majority, when this 90% of labels we can be certain about, and then we exclude the rest of the data, like this period of data. Actually, it's just like very like simple approach how you can tackle this, but in reality, there exist methods how you can predict basically what kind of these orders will change label in the future or not. And it's like on our backlog, maybe like to look at this method and implement it later. So basically, instead of just excluding latest period of data, you're trying to predict which of them will change label or not. And so you have like separate model which predicts label for your data. And then you are using this like most fresh data with predicted labels.
Thanks for the talk. What downsampling strategy to use for your training sets?
What downsampling strategies we use?
For your training sets, you said that you downsample the good customers, right?
We like use this undersampling, but it's just like random sampling from data set. So it's like nothing, just randomization, pure randomization.
Yeah, thanks. Just a follow-up to the gentleman's question about imbalanced data set. When you found that n-to-1 balance is better than 1-to-1, is that considering the cost functions of different false positives and false negatives, or is it just accuracy-wise?
I don't know, like we are choosing, the main metric which we are interested in is already like considering like everything, which I described there, and that's how we choose this like n number.
Okay, because then I guess the different cost functions could explain why you want more of certain kind of labels, or couldn't.
Interesting comment. Might be, but maybe not.
Okay, just like everything. Yeah, thanks.
Yeah.
I'll take a couple of online questions as well.
Yeah.
So, can you elaborate why you need this low latency? It's somewhat surprising for this application for fraud, I imagine. So essentially, why does it need to happen so quickly, the fraud prediction?
I mean, you everybody used kind of Bolt, and when you open your app, you want to like happen everything like smoothly. You want your driver to be in front of your door right away, and that's why like imagine yourself, you're waiting for a car to go to taxi, and then you wait for a couple of seconds, and we just like the orders are happening in real time, and the fraud prediction is just one like thing which is happening. There are other like models which predicts there, and it's all add up. And you mentioned like this 13 of models you like adapt to like to this maybe like 13 seconds. You want to prevent it. That's why low latency is important.
And I guess we don't want to dispatch a driver also to an order that is potentially fraudulent. So otherwise,
yeah, it's also
another one. Are you checking device ID for repetitive fraud transactions?
I mean, we use many like different features for our model, so kind of.
Very good. From here?
Hey, I saw like a lot of like emphasis on feature engineering and even some hand-written rules like on the graph, like bypassing the machine learning model. So my question is like, how interpretable are your models? Like, do you actually know like this was fraud, but why? Can you backtrack on your model, or is your model like basically a black box model?
So we are using a YGBM model, and it's like tree-based model. And for tree, you can get like high interpretability, and especially we are using chop values, like sharply values, and they allow you to understand what features are important or not, and you can order this feature importance, and you can see like which features influence to like which range your predictions. So our models are interpretable, and yeah, sometimes there are cases where we want to understand like why it happened, and then we can run model and we use this like sharply values, and it tells why this prediction was made. So it's not like a totally black box model.
Yeah, and the other question would be then, of course, that's probably the NDA answer, but what are the features that like are the most interesting, or it's probably something obvious, but.
Unfortunately, you answered that question. It's we cannot tell this information.
Great. So thanks a lot, Elisaveta, for this great talk.
Thank you.
We have one more prize to give.